Okay, so we'll pick up where we left off with the last video, and we know that we have the concentration and volume of HCl to start with, and we know that we need to get the pure mass of the sodium carbonate in order to use it in our final step. So the steps we need to take are these ones here, okay? So first of all, we work out the moles of HCl by doing the concentration times by the volume. Now you'll see here I've done 26.40 divided by 1,000, which is to get that volume from centimetres cubed to decimeters cubed. Okay, so don't forget, whenever you're doing concentration times volume, it needs to be volume in decimeters cubed. Okay, and that gives us the number of moles of HCl, which is 0.0066 moles. Now we can use the number of moles of HCl to find out the number of moles of sodium carbonate, and at this stage, all we'll be able to get from that is the number of moles of sodium carbonate in 25 centimetres cubed. Because remember, only 25 centimetres cubed of the sodium carbonate solution reacted with the HCl. So the moles of sodium carbonate in 25 centimetres cubed is going to be 0.0066, which is the moles of HCl, divided by 2, because it's a 2-to-1 ratio, where 2 moles of HCl react with 1 mole of sodium carbonate, and that gives me 0.0033. Okay? Now, slight complication here, and that's because we've got these two volumes. We have the 250 centimetres cubed, which is the total volume of solution, and we have the 25 centimetres cubed for sodium carbonate, which was the volume used in the titration. Now, if we're working out percentage purity, the mass we need has to be based on the total number of moles in that sample. And that means it's the total number of moles in that 250 centimetres cubed. But we don't know that yet. All we know for the moment is how many moles were in the 25 centimetres cubed that reacted with the HCl. So before we go any further and start calculating the mass for sodium carbonate, we have to scale it up and work out how many moles we've got in that total volume of 250 centimetres cubed. So I'm going to move us on to a new slide, and we'll just talk about how to do that. So I've given you a formula to follow here, and sometimes I think having a formula kind of makes this look worse than it is. And sometimes if you've got nice numbers like we do here, you don't need to go through and think about it like this necessarily. You might be able to just figure out straight away what's going on. But you don't always have nice numbers, and therefore I think it's quite important to have a formula so that you can follow it and figure out how to do the calculation you need to do, okay? So remember, we're trying to work out the total moles of sodium carbonate here. And right now, we know the titration moles. So that's what we were able to work out by starting with the number of moles of HCl that reacted with the sodium carbonate in the titration. So the titration moles we've got is 0.0033. But the total moles is going to be a lot more than that, because we took a 25 centimetre cube sample and did a titration with it, but the total moles will be all the moles in that full volume of 250 centimetres cubed. So with this calculation, for our example, the total volume is that 250 centimetres cubed. The titration volume is 25 centimetres cubed, and the titration moles is 0.0033 moles of sodium carbonate. So what we're essentially doing here is working out how many times bigger the total volume is than the titration volume. And then the number of moles in the total sample will be that many times bigger than the titration moles as well. So you can see here the total volume of 250 is 10 times bigger than the titration volume of 25 centimetres cubed. So the titration moles will also be 10 times bigger, and it'll work out as 0.033 moles of sodium carbonate in that total volume of solution. And this is what I mean about if you've got nice numbers, you might not need to go through and organise your working like this. You can just see that it'll be 10 times the titration moles. But if you get a weird volume like 250 centimetres cubed for the total volume and like 11.2 centimetres cubed, say, for the titration volume, it's good to have this to fall back on. Okay. Now, This step in the calculation pops up all over the place for lots of different calculations with chemistry, and that's another reason why I think it's so important to take that time to get yourself organised first, so that you can notice where you've got various different volumes and you can be ready to do this, okay? So this step here in bold, this is the one that we've just done. The moles of sodium carbonate in that total volume of 250 centimetres cubed is equal to 250 divided by 25 times the titration moles of 0.0033, and that gives us the total moles of 0.033 moles of sodium carbonate. Okay. Now we're almost ready to do that final step, because now that we've got the total moles of sodium carbonate, we can work out the mass of sodium carbonate. So the molar mass of sodium carbonate is 106. So if we do the total number of moles times by that molar mass, it will give us the pure mass of sodium carbonate. Okay? Now, we can put that into the final step, but before we do, let's just check in and make sure that this makes sense. Now, our pure mass should be smaller than the total mass. And you can see it is. The total mass is that 5.25, and our mass is 3.498. Now, that's good. If we got a mass, though, that was bigger than the total mass at this stage, then we know we've made a mistake somewhere. So for example, if you forgot to do the number of moles of HCl divided by 2 to work out the number of moles of sodium carbonate, then you'd end up with a mass that's bigger than the total mass. So that would be a way of catching your mistakes, okay? Other than that though, I think we're ready to go ahead and get our final answer. So the percentage purity is the 3.498 divided by 5.25 times 100, which gives me 66.6%, and that's the three significant figures. Okay, and there's our final answer. Now, just a note about the rounding. I've rounded to three significant figures there because that's what we decided when we were doing the organising stage. I did say we want to keep 4 significant figures in here though, but you'll notice at most stages we only actually have 2 significant figures there, okay? And that's because when I was doing this on the calculator, that's all it gave me, okay? I didn't actually have any extra significant figures, it just came up as nice round numbers, okay? So I didn't just put random zeros or make things up, I just kept it as what it was. However, at this step, the 3.498 there, I rounded to 4 significant figures because I had all sorts of digits on the calculator, okay? Now that's it. So hopefully you managed to figure out some of this by yourself when you had a go. If not, then think about where you went wrong. So was it that you weren't quite sure what to do with the volumes? Was it that you forgot to use your stoichiometry, etc.? Or was it that you worked out the MR wrong? Honestly, working out the MR wrong is responsible for more mistakes in calculations than you might think. And what I often find is that that happens because students are kind of doing the working in secret for the MR on the calculator and not writing it down. So they're not giving themselves a chance to catch the mistakes. Okay? So I think whenever you're working out your MRs, do write it down and make sure that you can give yourself a chance to see where you might be going wrong.